The second chapter of aircraft performance, we will have a look at the takeoff performance. The first part is takeoff procedure. At the start of the runway, the aircraft will have full engine thrust, so the pilot will set full throttle setting, and also the brake is released. And we can see an aircraft here, and it's stationary on the runway, and it's about to take off or start the ground run. And in this case, we have thrust acting on the aircraft, and also we have drags. And the drag has two components. One is an aerodynamic drag, the second is the rolling friction drag. So in total, the thrust should be larger than the aerodynamic drag and rolling drag together. When the aircraft is in acceleration, sometimes directional control is required on the runway. And of course, we can use a nose wheel when the speed is low. So it's like driving a car. We can change the direction by turning the nose wheel. And when the aircraft gains some speed, the rotor can be applied to change the direction also. Okay, so if we look at the aircraft in the center, and it's now nose to the left if we are viewing from the top and facing the fuselage, along the fuselage. So in this case, which direction does the rotor deflect to? And I give you 1 second to think about it. Okay, so the rotor should deflect towards the right-hand side, and this will increase the camber on the tail. So there is a side force towards the left be created, and this side force will produce a yawing moment, and so that will correct the direction of the aircraft, make it straight along the runway. And so now it's clear, if the nose to the right, we need to deflect the rotor towards the left, right? So this will create another side force and generate a yawing moment to make the aircraft straight along the runway. And remember, only when the aircraft has enough speed, the aerodynamic control can be applied. That's using a rotor. Otherwise, there won't be enough side force produced, and also not enough yawing moment to correct the direction. We know on the ground run there is a possibility the engine fails, and this is a condition we also need to consider, and especially for the directional control. And we know if one engine fails, if it's a multiple engine aircraft, there will be thrust asymmetry. Okay, so if we have this aircraft, the top view, the left engine fails, and we only have thrust from the right engine, and this thrust T will create a yawing moment, and so the aircraft will heading towards the left, right? And as we discussed earlier, we can use the rotor to control the direction. So the rotor in this case should deflect towards right. This will produce a side force acting on the vertical tail, and that will correct to counteract the yawing moment N. So this side force Y will generate a yawing moment to counteract N from the thrust on the right wing. So left engine failure, nose to the left, and the rotor deflected to the right. And okay, so if right engine fails, we only have thrust on the left wing, and in opposite, we just deflect the rotor towards the left. So right engine failure, nose towards the right, so the rotor deflects to the left. So that's how the rotor deflects to have the right directional control. And there's one velocity we need to bear in mind. That's the minimum control speed on the ground. And this airspeed is when sufficient aerodynamic forces are produced by the rotor to enable aircraft to maintain straight course with zero yaw, with one engine inoperative. So this one is related with the situation when one engine inoperative, OEI. And so if it's the aircraft is flying, or not flying, is moving at a speed larger than this, it can still take off. But if the speed is less than the minimum control speed, the takeoff should be aborted. So on the OEI, even though nose wheel steering or engine thrust moderation could make a contribution to yaw control, but the airspeed is less than this minimum control speed, then the takeoff must be aborted because the rotor could not generate enough correction yawing moment to maintain the direction of the aircraft. And in this slide, we'll look at the elevator control on the runway. Just now we've seen the rotor control for the aircraft directional maintenance. So in here, we are looking at the elevator control. We know elevator controls the pitch of the aircraft. And let's see how it works. So the first phase in the ground run is acceleration. And at this moment, the aircraft altitude is at the lowest possible angle of attack. And the benefit of by doing this is there's no lift generation needed because it's still on the ground. And because of the lift is small and the angle of attack is small, there will be small aerodynamic drag due to the small angle of attack. So that's a benefit we need to know. And at a moment when the aircraft gains enough speed, it will rotate to nose up. And how do we make the aircraft rotate to nose up? We need to apply the elevator. So the elevator needs to be deflected upwards. In this case, there will be a vertical force now, Z, pointing downwards, and this downward force will create a pitching up moment, M. So elevator deflection up to make the aircraft to pitch to nose up, and this is because of the pitching moment produced by the elevator. And we should remember this speed, the speed of the aircraft at this moment, nose up, is called rotation speed. Why rotation speed? Because the aircraft starts to rotate and the angle is, or the angle of attack is increasing. And after the rotation speed, the aircraft, although the nose wheel is lifted off the ground, but the rear wheels are still on the ground. So it will continue to accelerate after rotation speed. And finally, the aircraft will lift off from the ground. And so that's the completion of the ground run. All the wheels will leave the ground. And we call this speed the lift-off speed. And lift-off speed is related with stall speed, and the relation here tells us how to calculate the stall speed. We have W equals half rho v squared times S times CL max, and we know the CL increases nearly linearly before stall happens. So we use CL maximum. So that's a borderline. If it's larger than that, stall will happen. So we use its borderline magnitude CL max, and that's on the right hand side is a lift equals the weight of the aircraft. And then we can make the speed explicit, and we call this speed stall speed. So to maintain some margin before stall happens, so the liftoff speed should be larger than 1.2 times of the stall speed. There is a possibility when the aircraft is over-rotated at this rotation speed VR, and this will give rise to these two consequences. One is the liftoff might be too soon, and the second is the aircraft might climb at too low an airspeed. So these two consequences happens if the aircraft is over-rotated. So there should be a maximum limit of the rotation while the aircraft is still online, and this gives rise to the minimum speed aircraft becomes airborne, and there is a speed associated with this maximum limit of rotation. We call it VMU, and it's essentially the minimum on-stick speed. So the test of VMU is part of the certification test, and you can imagine if the aircraft is over-rotated, one consequence is the tail makes touches with runway. So in the certification procedure, the aircraft will be tested with a runway with the lowest part touching the runway, and you can see if the aircraft will catch fire or it will harm, destroy the structure. And in this slide, we will see a few other important speeds during the takeoff procedure. So the first is the decision speed V1. We will look at this speed later when we study the balanced runway length. Okay, so under one engine inoperative condition, OEI condition, the decision speed is very important on the OEI. If the aircraft has speed is less than V1, so the takeoff should be aborted. But if it's larger than V1, because the airspeed is great enough to allow like direction control by the rotor, right? So the aircraft can still take off. So the takeoff continues, and the pilot will find a solution once it's airborne. Okay, and there are also V2 and V3, and takeoff safety speed V2 with OEI or V3 with AEO. So V2 is for one engine inoperative, V3 is for all engine operating conditions. And a safe climb rate and the direction control can be achieved at V2 or V3. There is also minimum control speed airborne. And remember, if in the slides before we had VMCG, minimum control speed on the ground. So in here we have minimum control speed airborne. So that's VMC. And the reason for that is the undercarriage wheels can no longer provide any directional control. So VMC should be larger than VMC on the ground, minimum control speed on the ground. And there is a moment we can decide the completion of takeoff. And when the aircraft lowest part clears a screen height of 35 feet or 10.7 meters, and that's the screen height. If the aircraft is the lowest part is higher than that, we can conclude the takeoff procedure. Okay, in this slide, we are comparing or listing all the important V-speeds we introduced in the previous slides, and you can see from the very left-hand side is 0. That's when the aircraft is static. And then we have first VMCG, minimum control speed on the ground. And after that, we have VS stall speed, and then we have V1 decision speed. And after that, we have the VR rotation speed. And then we have VMU, minimum on-stick speed. And finally, we have the liftoff speed. After the liftoff, the aircraft will leave the ground. So the final phase is V2 and V3. That corresponds to when the aircraft is higher than the screen height.